much for your presentation. So now we are going to go to our last presentation of the 2020 ISESSAH conference, and that will be Dr. Norhariani Mohd Nor Yani. She obtained her PhD from Utrecht University in the Netherlands on the economics of heifer rearing on Dutch dairy farms. She's currently a senior lecturer at the Faculty of Veterinary Medicine at the University of Puerto Malaysia. Her current research interest is on the economics of dairy heifer rearing in Malaysia, developing precision veterinary surveillance systems for dairy calves, the economics of vaccinating against vibrosis in marine cage farms, and the socioeconomic impact of antimicrobial resistance on shrimp farms. She specializes in estimating costs using stochastic bioeconomic models in at risk. And today she will talk about some of her work on looking at Asian sea bass using some stochastic modeling.
Thank you very much, Dustin, for the introduction. Thank you, everyone. Good evening. It's actually 10 o'clock here in Malaysia. So this research is funded by the Ministry of Higher Education in Malaysia, as well as University Putra Malaysia. And the topic is about estimating cost of vibrosis in cage culture of Asian sea bass. So this research is conducted with the aim to actually knowing the cost and benefit of vaccinating against vibrosis. But before we do that, we will need to actually estimate the cost of vibrosis itself. And this research has been published, and there were two things that I did. First one is the survey at marine cage farm, and the second one is building the model. And for this presentation, I will only describe the second one. So aquaculture is one of the major contributors to the economy and food security in Malaysia. And aquaculture is actually challenging, and also it is due to the uncertainty in weather, and as well as there are different seasons in Malaysia. And this probably could cause lower production and value of the brackish water cages in the recent years. And these are the socio-economic activities at cage culture farm, which consists of managing the business, managing the farm, as well as managing the animal health. And we are interested in knowing the cost of grow out of Asian sea perch, or also known as Asian sea bass. And as you can see, the Asian sea perch got its name from its dorsal fin, which can pierce to the other fish, and especially when you are trying to do activities such as grading, so that increases the risk of vibrios on the cage farms. So most of the small scale farms actually do not know the cost of grow out of Asian sea bass. And one of the most important disease in cage culture is vibrios, other than other viral diseases. And in Malaysia, the outbreak was estimated to be $5 million US. And so little is actually known on the economics of cage culture in Malaysia. Especially we are talking about the endemic disease such as vibriosis. And in order for us to estimate it, it is actually difficult. There are several things such as the variation in growth, uncertainty in disease, and difference in farm management. So I would like to demonstrate how we did the estimation on cost of rearing an Asian sea bass. in marine cage farm in Malaysia using a stochastic bioeconomic model. And this is how the model looked like in the Excel. So as you can see, we try to predict the status of the animal from the first day of the grow out until 196 days post stocking. And on the first day of the stage, we try to estimate the cost of fingerlings, the feed costs, the labor costs, and if there is the preventive measures cost. We also included that in the first stage, and that started from the 4-inch fingerlings. And then on the second stage, we estimated the feed cost, the labor to feed the fish, labor to clean the net maybe, and some other work. And then we estimated the cost until the market age, which is at 32 weeks, or it is actually at 1 kilogram. The model is able to predict when the fish is infected with Vibrios subclinically and clinically and die due to Vibrios. So we estimate that cost as well. And so the first stage, we estimated the fingerling costs, feed costs, labor costs, and preventive measures costs, and then feed, labor as well as the same. And then if there is clinical Vibrios, then we add on the cost of treatment and maybe diagnosis costs. And then if it's dead, so we stop the calculation until at the age. So at each stage, that box, we have a transition matrix where we try to predict that status basically from the previous stage to the next stage. And we need information such as the prevalence of subclinical and clinical vibriosis, as well as death due to other causes. And for instance, if in previous age it was healthy, then the next stage it have the probability to become subclinical vibriosis or die due to other reason. Or if it's subclinical vibriosis, it can be cured or die. And in the case of clinical vibriosis, it had a probability of dying due to Vibrio. So the inputs for the prevalence was taken from a farm in Selangor, which is the west coast of Peninsular Malaysia. It was done by another team. So they sampled the fish for a year, and they found that there was a different type of Vibrios, but mainly Alginolithecus, Vulnificus, and Harveyii. And then we search for literature on the case fatality rate and the number of dead Asian sea bass due to other reasons. And both are validated by the experts. And then we also try to find the inputs from the literature because we are unable to get those some of the information from the farms due to lack of recording. And the body weight was actually a growth curve published by Glencross, and it uses information such as temperature to predict the body weight. In case of antibiotic, we assume that there is a use of antibiotic under the prescription of veterinarians, although we know that might not be the case, and we only assume that we use oxytetracycline, which is allowed in Malaysia still. And then we have some information on the number of samples being sent to the university laboratory. So we estimated that cost as well. And then based on our survey results to 62 cage farms in Peninsular Malaysia, so we take those prices. And then based on this model 78.7% of fish that was simulated survive and reach the market age, and the mortality rate due to other causes was 14.4%, and due to vibriosis at 6.89%. And the average total cost to produce a tail of Asian sea bass was estimated as at 12 ringgit and 80 cents with a variable cost, which is feed cost, labor cost, and we also have a bit of fixed cost there. And then the mortality cost, which include other causes or vibrios. So in total, it was 14 ringgit 71 cent, or $3.61. Because we did a survey in Asian sea barge cage farms, so we are able to validate our result. Might be lower a bit because they use less pellet, because it's a combination between pellet as well as trash fish at cage farms. But overall, it looks more or less similar. And then the total cost was of vibriosis was estimated as 99 cents per tail per kilogram, which is 24 cent US dollar. And mortality is the highest cost, followed by treatment costs, and then a diagnosis cost. And because we did survey, and we found that to produce 1,500 tails of fish, the survived one, it cost them around 19,000 ringgit Malaysia per cycle. So if you times 1,500 with 99 cents, you get that 1,481 cents. So there was an additional 7.8% of additional cost per cycle. In this study, it was not easy to put in prices of costing, because it is difficult to obtain farm management data. The ones that you saw is really a very, very good farm records, and they did it because of they might get good aquaculture practices. I'm not sure if it's being analyzed. So there is a need to have more information or data on that, as well as the information on the water quality, because that is also one of the things that can predict Vibrios, as well as disease prevalence at different areas. For now, we only have data from the west coast of Malaysia. So we actually have finished looking at the prevalence of Vibrios at the east coast of Malaysia, and probably we will include that information in our current model, as well as include maybe some probability of an outbreak there. And in addition to adapting it for the East Coast, we're gonna have additional costs from the risk from the hatchery. And another work that we're going to do is answering the impact of vaccination against Vibrios. So in that, my conclusion is that the average cost of Vibrios in Malaysia is 99 cents per tail, and it can increase the cost of production by 7.8% per farm per cycle. And with that, thank you very much. Open for questions.